All right, we've got a small group here today.
Yeah.
I don't know if that picked up on camera. Okay, so the first order of business. Last class I handed out your take-home exam, right? And I decided I'm going to change problem number 3. I've already changed it online, but I'm going to hand you a whole new, fresh copy of number 3. And the reason why I'm changing it is because originally when I made that problem, the instructions were to set up the integral but not evaluate it. And it's practically impossible to evaluate by hand. So I made a problem that you will be able to evaluate by hand. There enough there. Here, you take a couple of these extras. Yeah. Okay, that's the only thing that's changed. Problem number 3. All right. Originally, I believe it was a sphere, so it changed. Everyone got that? Number 3 is changed. Extra. There should be another here.
Yeah, you change one problem.
All right, let's get started. Yeah, I changed it online also today. I didn't send an email, but the files online have been changed. All right, so today we have a lot of work to do. We're a little behind right now, and so I'm not going to try and go too fast, but I do want to kind of pick up the pace. We're going to do double integrals in polar coordinates today, chapter 12, section 3. I was at that number 8. Yeah, anyone else who did number 8, you can turn that in. I have not had a chance to grade your mini exams yet. I'm still working on those, so. All right, so we're going to do double integrals in polar coordinates. So right now we have talked about double integrals over 3 types of different shapes when it comes to talking about the domain. We first started with the double integral over a rectangle. Then we had this type 1 region where our x's were bound between 2 constants and our y's were bound between 2 functions of x. Then we did a double integral type 2 region, which was our y's were bounded between 2 constants and our x's were bounded between 2 functions of y. Right? So that's what we have done. And now what we are going to do is look at some more interesting regions that we can't easily describe using our Cartesian coordinate system. So first, let's remember that if somebody gives us a point in 2-dimensional space, it must have an x and a y coordinate, right? And the way that Cartesian coordinate system works is that we start with a place that we call the origin. From the origin, we construct 2 axes, the x and the y axes. These 2 axes are orthogonal to each other, perpendicular, right? And then to describe a point living in a Cartesian 2-dimensional space, the x and y values tell us how far we would travel in the direction of the x-axis and then the y-axis respectively. So if this was 2, 3, this would mean go out this way 2 and up 3, right? That's Cartesian coordinates. And when you're in 3-dimensional space, it's x, y, z, right? And you have 3 axes in 3-dimensional space as opposed to 2. So in order for me to describe a point in 2-dimensional space using Cartesian, I need 2 things, don't I? X and y. But there's another way to get to that same point that eliminates the need for the x and the y axes. And that is, if I want to get to this point, I can instead point out this direction, still in the direction of the x-axis, and tell you how much to turn by. So I tell you, turn by this angle, and you rotate, and then I say walk out a certain distance, which would be r, and that would take you to the same point x, y, wouldn't it? So there's 2 different ways we could get to that point. Cartesian, x, y, or this other thing, which we call polar coordinates, which gives you an angle and a distance to walk. So we know from pre-cal, that there is a relationship that we can establish between the x and y coordinates and the angle and the radius or the hypotenuse of this right triangle, right? So cosine of theta would be x over r, sine of theta would be y over r, and if we mess with those equations, we come up with that x is r cosine theta and y is r sine theta, right? Remember that from pre-cal? So this polar coordinate system, in order to define a point, you still need two things, right? What are they? Theta and r, right? You give me theta and r, I'll tell you where I'm going to be. You give me x and y, I'll tell you where I'm going to be. So both Cartesian and polar require two inputs, but it's just those inputs have different meaning, right? Questions? Change the radius, right? Change the angle. I can get to any point I want, right? Like that. All right. I think this is a little too big. Let me go smaller here. Just want to make sure I'm recording. See a red dot up there? Yeah. Okay. All right. As we continue here, let's set up some relationships that we have. I can barely fit that on there. Let me make this a little smaller so this all fits. There we go. That didn't work. There. Okay, so the relationships we have from the right triangle Pythagorean equation, right? X squared plus y squared is r squared. So that's a relationship between x, y, and r. What we're trying to do is we're trying to figure out a way to go from Cartesian coordinates to polar, or from polar back to Cartesian. So these are the relationships that we're going to be using here. This equation, of course, the relationship between x, r, and theta is this from pre-cal, between y, r, and theta from pre-cal, and then there's one more from pre-cal that if you want to know what the angle is, you can take arctangent of the y coordinate over the x coordinate. And just remember on the arctangent, you have a domain restriction. Your domain restriction for arctan is between negative pi over 2 and pi over 2. So those are the main relationships between Cartesian and polar coordinates. So remember that when we were talking about a rectangle in Cartesian coordinates, what we were saying was that we had this interval AB crossed, even though we said it wasn't cross product, crossed with the interval CD, that this was the restrictions on x's, this was the restriction on y's, and we drew this rectangle, right? That's a rectangle in Cartesian coordinates because it says our x is bounded between two constants, our y is bounded between two constants. But what would a rectangular polar region look like? So instead of your x and y being stuck between two constants, what if your theta was stuck between two constants? Because, right, polar, you need theta and r, right? So what if your angle's stuck between two constants? We like to use alpha and beta as our constants, a, b, right? But in Greek letters, alpha, beta. And then our r is stuck between two constants. We use the regular script a and b, a, b. So what would that look like? Circle? Let's see. Here's what it would be. So let me change first of all the angle. Okay, the alpha is the small angle, okay, the first angle. So I'm going to go from here to beta, which would be that angle. So that's where I start. I want to swing through that angle and stop at this angle, right? And then my radii, because there's two of them, my smallest radius is how far I walk out, right? I can adjust that. And then my outer radius, I can adjust this. Did y'all see that object? This is a rectangular region in polar coordinates. It doesn't look like a rectangle, right? Not a traditional rectangle. All right, with me? So remember from double integrals, when we first started, we were integrating and we were doing Cartesian coordinates, we weren't even talking about polar yet, but the way we set it up was we said that this little differential dA, right, represented this infinitesimal little area, which we got by putting dx and dy and multiplying, right, because area is, width times height or length times width, however you want to say that, right? And this right here, this little dA, is a rectangle in Cartesian, right? So if we do a double integral in polar coordinates, our dA is going to have to be a rectangle in polar coordinates, which we just saw what that looked like, right? So take a look at this. This is kind of a complicated picture, all right? If we want to do a double integral of some function of r and theta instead of x and y over some region r with respect to area, then we need to know what the area of that red piece is. It's not as simple as the area of a rectangle back in Cartesian, right? It's not just length times width. Yes? Okay, so let's try and figure out what this would be. There's something you have to remember here from pre-cal again, excuse me, that if, how many of you remember this formula? What's that? Arc length, yes. So you remember that formula? S is equal to r theta. This is if you start here and you swing through some angle theta, then this arc right here, S, and if this side was r, then S would be equal to r times this angle. Remember also from pre-cal that angle had to be in radians for this to work. So we have ways of measuring arcs, right? Okay, so with that knowledge, if we're trying to take an infinitesimally small little polar rectangle, we need to know its area, then do you agree that it would be approximately the area of that rectangle? Do you see that? Now it's not perfect, right? We have some error in there. But as this gets infinitesimally smaller and smaller and smaller, doesn't this area get small? I mean, this error, E-R-R-O-R, doesn't that error basically go away? Yes? So in the infinitesimal, this error is negligible and in fact goes to 0. So if we can just find a formula for that, we'll be good. So what we use is, for this side of the rectangle, we use this arc length. And then for this side over here, we just use this length. Okay, yes? Now remember, in a polar rectangle, as you swing this way, that's your angle changing, right? As you move out like this, that's your radius changing. We have two variables, r and theta, instead of x and y. So if I want to measure this side right here, this will be how much my radius changes, doesn't it? Isn't it? Yes? So I call that dr, just like dx was a little infinitesimal change in x. But this piece right here is not d theta. That's what a lot of people think. Well, that's just d theta. No, d theta is a measurement of the angle, isn't it? You actually need the length of this arc. And so you measure from here to here. We call this r, right? If this is d theta, then we're right back to this picture, r, but then this is d theta. So the length of this little arc would be r d theta. Understand that? Yes? Okay, so dA becomes r dr d theta. These three things multiplied together. This times this, yeah? And it doesn't matter what order we do this in. Questions? So here's the summary. If we want a formula for a double integral over a polar region, where our region is defined as all points in two-dimensional space given by r theta. Now be careful, r theta here is not an x and a y, right? It's a distance you walk and it's an angle you turn. It's all the points defined by those two conditions where your theta is between alpha and beta, your r is between a and b, It's still the double integral that we had last class over r with respect to area, but I'm going to change x over from Cartesian to polar. And we said that the relationship between x and polar is that x is equal to r cosine theta, isn't it? Yeah? And that the y changes from y to r sine theta. Our dA, we just showed in the previous picture, was r d theta dr, right? Didn't matter what order that was in. And then our limits of integration were alpha, beta, and a and b. Do y'all follow that? The important thing, the major important thing, is that if you ever have a problem that's Cartesian and you convert it over to polar, you will always have an r appear in your integrand. The r will always pop up. Later on, we're going to see that comes from a formula, but for now, okay, just remember that for polar, the r's there. That's the biggest mistake I see students make. They go from Cartesian to polar, they do everything correctly, they set up the integral, they forget the r. So we're going to do this example here. Find the volume of this. Find the volume under z equals 3x plus 4y squared on the region bounded by x squared plus y squared equals 1, x squared plus y squared equals 4, with y being greater than or equal to 0. All right, so just like before, what we want to do is draw the region first. Okay, so let's draw our region of integration. My region of integration is bounded by this circle, right? That's a circle. And this circle. And y has to be greater than or equal to 0. So x squared plus y squared is 1 is the unit circle. And then we have x squared plus y squared equals 4, which is a circle with radius 2. And finally, y must be greater than or equal to 0, which means that we're only looking, what, above the x-axis, right? So everything above this x-axis. So do y'all see the region we're talking about? Yeah, bounded by all three. That's it right there. Now let me ask you something. This problem has said nothing about polar coordinates, has it? I could have given you this problem last class. Could you do this problem using what we've done? Like, does that fall into one of the categories of a type 1 region or a type 2 region? So you remember what we did to do this? We just drew a little arrow. And we need to make sure that if we're going to do type 1, the arrow was vertical. And that as we move that arrow left and right, that the top and bottom bounds always stay the same, right? So what if I draw an arrow right here? That top blue one, right, is always going to be on top there. And then the green one is on bottom until I get to the red. And then it switches, doesn't it? Like if I move this arrow over here, the top one's the blue, the bottom one's the red. Now, see how it's switched? And then once I get over here, past this point right here, then it's going to switch again, isn't it? So I could do this as a type 1 double integral from last class, but I'd have to break it up into 3 separate regions to do it. Do you see it? Okay, so I'm not a big fan of that, especially if I realize that this is a polar region. This is a polar rectangle, isn't it? So in terms of this region, give me that in polar. What is the restriction on theta and the restriction on r that would draw that same region? So how about theta? How are you going to draw all the points in here? Yeah, you're only allowed to point between 0, right, to pi. And then as far as the radii are concerned, the minimum you walk out is what? The smallest that you can walk out would be to get to the red, right? So you walk out, what, 1 would be the smallest? And then the most you could walk out would be 2. Does that make sense to you? You're taking all points where you're turning between 0 and pi, and you're walking out between 1 and 2, and it should draw this shaded region in here. Okay, so we've got the region under control, I think. What is the function f of x, y that we are going to integrate? It's this right here, right? Solve for z, but it's already solved for z. So 3x plus 4y squared. I'm trying to do this double integral right now. I've already convinced myself that the region is better suited for polar than it is for Cartesian, so I need to convert this from this to polar. To do that, I have to evaluate the function instead of at x, at where? X is replaced with r cosine theta, and here y is replaced with r sine theta, and then dA is r dr d theta. Now, this does not matter. Right now it doesn't matter because what? This order doesn't matter why? They're both the theta and the r are both restricted between constants. And from the first time we talked about double integrals, if the two limits of integration are constants, the order of integration can be flipped. So I could put r dr d theta, or I could put r d theta dr, but then that would determine which numbers go here. Okay? No questions yet? Okay, let's go ahead now. Let's take the function. Let's replace all x's with r cosine theta. Let's replace all y's with r sine theta. And let's rewrite that right here in the double integral. So it'll be double integral. I'll leave it as r for now. Let x go in there. So it'll be 3 r cosine theta. Agreed? That's 3x plus 4 times r sine theta squared. So how about r squared sine squared theta? Then r dr d theta. I need to put my limits of integration over here. I probably should have done that already, but my order of integration, I'm going r is the inside, theta is the outside, so I should have what on the outside integral? 0 to pi, and then 1 to 2. And that'll be the integral I need to figure out. So integral, double integral, 0 to pi, 1 to 2. I'm going to rewrite this. I'm going to distribute the r through. Is that okay? 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. And that's it. Now we just tackle this. Any questions? I'll go ahead and do this one. I'll finish it out. All right, let's first integrate with respect to r. By the way, you could split this, all right? I don't know if anyone's noticed this, but you could do 2 double integrals because you have addition. And then this double integral right here, since r and theta are separated by multiplication, you could break that into 2 integrals being multiplied. I'm not going to. I just want to point out you could. So here, what is the antiderivative of this thing with respect to r? So r cubed cosine theta plus r to the 4th sine squared theta. That's your antiderivative, right? I'm evaluating that where and where?
2 to 1. R equals
r equals, right? R equals 1, r equals 2, like that. And then d theta out here. So we're going to plug in 2 first, figure out what happens, subtract what we get when we plug in 1 for r. So we have integral 0 to pi. Let's see, we should have 2 things here. So what happens when I plug in 2 for r? 8 cosine theta plus 16 sine squared. So 8 cosine theta plus 16 sine squared theta. And then when we plug in 1, we get cosine theta plus sine squared theta. And now we can clean that up. So we have equals integral 0 to pi. How many cosine thetas do we have? 7 of them. 7 cosine thetas. And then 15 sine squared theta d theta. And now we're back in Cal 2. So I think the first one's pretty straightforward, right? Antiderivative of this is straightforward. How are you going to handle the antiderivative of sine squared? What's that? U sub? What would your u be? We're not doing that, right? That's done? We don't have to worry about that? No? Power reduction formula. Power reduction formula. Remember this formula? We had 2 of them. It was cosine squared theta equals 1/2 plus 1/2 cosine 2 theta. Then the other one was sine squared theta equals 1/2 minus 1/2 sine 2 theta. Those look familiar to you? Should have used those in Cal 2. So I'm going to use this one right here. Oh, wait, hold on. Oops. Sorry. Cosine. The only difference between the 2 formulas is a plus here and a minus here. All right, so before I do the integration on this one, I'm just going to rewrite the whole integral. And I have 7 cosine theta, and then plus 15 times this, but that is this, right? So distribute a 15 through here and here because it's 2 terms. So I should get 15 halves minus 15 halves cosine 2 theta d theta. Now each one of those should be pretty clean. No questions? Antiderivative of 7 cosine theta is 7 sine theta. The antiderivative of 15 halves theta. Antiderivative of this, what's the antiderivative of cosine 2 theta? 1/2 sine 2 theta, but then hit it with that. So negative 15 over 4 sine 2 theta. Evaluated theta equals 0. Theta equals pi. All right, let's plug pi in first. I think good things are going to happen here. Sine of pi is 0. Sine of 2 pi is 0. So that's all going to 0 out, but we'll have 15 halves pi, won't we? So 15 halves pi minus, now let's plug in 0. And I think everything zeroes out here, right? Sine of 0, sine of 0 is still 0. 15 halves times 0 is 0. So that's it, right? 15 pi over 2. Yes.
You remember how last class we did the type 2 region,
Mm-hmm.
and we switched the inside and the outside bounds
The inside and the outside bounds.
on the double integral?
We switch the inside and outside bounds.
Yeah, it should be right.
Uh-huh. I think I know what you're saying.
Switching the order of integration.
Yeah, that. So is that gonna happen ever with polar?
Oh, you mean like, yeah, you mean like we had an integral and then from the double integral we drew the region and then we switched it from type 1 to type 2 and then
because we had like.
we are not going to do that in polar.
So this is always gonna be it.
Well, we are going to do a type 1 region in polar, but we're not going to do a type 2 region. So we won't be able to switch from type 1 to type 2 because there won't be 2 to compare it to.
Right.
Yeah. Okay? What do y'all think of that? It's kind of neat, huh? Here's what we did, by the way, just so you can see. Here's our integration region in three-dimensional space. Here's the surface that we were integrating. And just that region plugged into the surface gave us this. Whoa. Okay. And then if we bring in the solid that we were talking about, that we tried to find the volume of, it's there, and I'm going to take everything else out. So you can see that this solid that we found the volume of, part of it was above the XY plane, part of it was below. But it looks like there's more above than below, right? So we should get a positive volume, and we did. We got 15 pi over 2. Find the volume bounded by the paraboloid z equals 4 minus x squared minus y squared and the xy plane. So this is a paraboloid. Paraboloids look like bowls, don't they? But this bowl actually opens the other way, and you can tell because you have negative coefficients in front of the x and the y variables. So if I were trying to get an idea of what this looked like three-dimensionally, right? If I'm trying to graph that in 3D, if x and y were both 0, my z would be what? 4? And then what about if what if y was 0 and x was 2? If y was 0 and x was 2, wouldn't I be 0? So if x is 2, y is 0, I'm here. If x is 0 and y is 2, I'm here also, right? My z would be 0. Now this extends backwards like this also. If I go 2 backwards, negative 2 on x, and y is 0, I'd be here. And if x is 0 and y is negative 2, I'd also be here. Do y'all see that? So here's your paraboloid. I mean, it comes down like this, goes in the back like that, comes over here like this, comes out like that. And what should it be on the ground? What should the shape be on the ground? A circle, right? And the way you know that is just let z be 0. If z is 0 here, right, you're forcing that thing down to the ground. And if I let z be 0, then that equation 4 minus x squared minus y squared must equal 0 is the same as 4 equals x squared plus y squared, which is a circle of radius 2. So this should be a circle on the ground, right? So y'all see that? I'm trying to find the volume, right, bounded by that paraboloid and the xy plane. So it's that object that I just drew there, right? So what is my region of integration? What's the floor that I'm integrating over? It's this circle, right? So I'm going to draw the region of integration over here. right? It's that entire thing. And I could do that maybe as a type 1. It might be messy because circles aren't functions. So, but if I convert this to polar, I think I can handle that. What would my restrictions be? I have to find restrictions on both theta and r. 0 to 2 pi, right, would rotate me all the way around. And then my radius should go from 0 to 2. I'm curious about your reaction to this. What's that? Well, what does the red draw? Does it draw half a circle? Let's talk about the black one first. The black one, I can point out any angle between 0 and 2 pi, right? So I point out here and I can walk out anywhere between 0 and 2. So it's everything on that line segment. I rotate a little bit, do it again. All the way around, keep going, I draw the whole circle, right? That's what this says. What does this say? I'll use a red marker. This time, I face out between 0 and what? Only pi. But I'm allowed to walk out -2. So if I'm standing here and I walk out to the right 2 and backwards 2, I draw the entire x-axis, right? Right here? This little segment, not the entire thing. But now what if I rotate just a little bit? I'm going to get this part and this back part. And I do that, I come up all the way up here. I get this part and the part below. So I basically have shaded out so far this part, right? Just by rotating that much. And if I rotate another 90 degrees, I'm going to get this back part also. So there's actually multiple ways you could do this problem. You could, does that make sense? Normally we don't like our radius to be negative though, right? The radius is like how far out you walk, but there's nothing restricting us from making our r negative. Now normally we don't do that, but it can be done. I mean, you can still work it out the same way. All right, we've got our region. Okay, so the next thing we would need is we need to be able to define our function of x and y converted over to polar. So what is f of xy here? It's got 4 minus x squared minus y squared, right? Now if I go to polar, that means everywhere I see x, I replace it with r cosine theta. Everywhere I see y, r sine theta. So if I'm going to switch this over, f of r cosine theta, r sine theta, it would become 4 minus r squared cosine squared theta minus r squared sine squared theta, right? That's what that would become. And what can you do with that? You can factor an r squared out of each of those, right? How about a little bit more? How about a negative r squared out of both of those? What would you be left with? Cosine squared theta plus sine squared theta, which is 1. So this is just 4 minus r squared. Now you could have noticed that beforehand had you rewritten this as 4 minus x squared plus y squared. And do you remember when I was showing you relationships between Cartesian and polar? I said one relationship we had was x squared plus y squared was r squared, right, from the Pythagorean identity. That saves you a little bit of trouble. So anytime you're doing a problem and you're converting from Cartesian to polar and you see x squareds and y squareds together, you can be thinking, can you get that to turn into a 1? Or sorry, can you get that into r squared, I should say. All right, so you ready to set this double integral up? It's a double integral. I'm going to go ahead right now and write r dr d theta. I'm going to write that right now because I know when I go to polar, I'm always going to have r. Then dr d theta, I have choice there in the order, but I'm just going to stick with that. That means my theta is going to be the outside limits. 0, 2 pi is what we're using. And my radius is the inner integral, so the limits there were 0, 2. And then what we are integrating, 4 minus r squared. Bam. We're done. That's not worth integrating any further, right? Distributing r through 4r minus r cubed. Integrate, that should be pretty clean. Can I dot, dot, dot this one? Equals dot, dot, dot. That is significantly easier than doing it the other way, which would have been to somehow break up that circle into type 1 regions from last class Cartesian. It would have been a disaster. All right, questions, comments? Y'all look tired. Some of y'all are falling asleep. Please don't fall asleep. Go do some jumping jacks outside or something. I know y'all are like on Easter sugar overload or something, but I am too. I stayed up last night way too late watching, what was that movie with, what's his face? DiCaprio. He's out in the woods all messed up. Yeah, I don't know if I cared for that. I mean, it was okay. I was expecting a lot more. I don't know, I was expecting a lot more. I mean, it was okay.
I mean, the guy won an Oscar for it.
Yeah. It's all right. I was a little let down, though.
I don't know, maybe you're thinking that he deserved
The real guy who went through that deserves it. Wasn't that a true story?
it.
Okay, I'm going to leave this problem on the board, but I'd like for us to do a pretty amazing problem. I think this is a great problem. We'll see. Verify that the area of a circle radius r is pi r squared. We all know that the area of a circle is pi r squared. Those of you who've had me for Cal 2, I verified this in Cal 2, but we did trig sub to do it. We're going to do it with a double integral now. So one thing we have to remember is something that we talked about last class. If you want to find the area of some region, capital R, it's equal to the double integral over the region of what function? 1 dA. That I told you in class last time, is that if you replace the function in here with 1, then the double integral of the constant 1 function over some region R is actually equal to the area of that region. Let's use that right now. Okay, what I want to do is find the area of a circle, right? So the region, that's going to be my region. So let's draw it. An arbitrary circle, radius r. That would make a wonderful polar region, wouldn't it? In fact, in polar, my restrictions would be very nice. Theta's between 0 and 2 pi, and r's, ooh, this is r. R is between, we have trouble here. Do you see the trouble we have? I got to use a different r. So why don't we call this, I don't want to use capital R to confuse it with region. I'm just going to use r tilde, all right? R tilde, this is a constant. See, our r here is our region. We're allowed to move through different radii values. So that r that I'm allowed to move through must be between where and where? 0 and r tilde. Everyone understand r tilde is a constant? I could have called this R naught. I could have called it anything I want. I chose R tilde. All right, set up the double integral. What does it become? The area of that circle over that region R should be equal to the double integral. It's polar, so I always have to put what in polar? RD, so I'm doing 1 R dr d theta. What's my restriction on R? So I can put that in there and my restriction on theta. Right here. So theta goes on the outside, 0 to 2 pi, and 0 to R tilde. Now, I could dot this one, but it's worth us finishing, right? Okay, what's the antiderivative of R with respect to R? 1/2 R squared. I'm going to evaluate that from R equals 0 to R equals R tilde d theta. Replace R with R tilde, replace R with 0. What would you get? Just 1/2 R tilde squared d theta. And now integrate this with respect to theta. This is all a constant, isn't it? So the antiderivative of that is 1/2 R tilde squared times theta. Evaluated theta equals 0 to 2 pi. Replace theta with 2 pi, replace theta with 0, and you get 1/2 R tilde squared times 2 pi. So that's just 1/2 R tilde squared times 2 pi, which is just pi R tilde squared, which is basically what we were trying to show, is that the area of a circle is pi times the radius squared. All right, so some of y'all are real tired or something because, I don't know, we just proved the area of a circle is pi r squared and y'all didn't seem too excited about that. So that's not going to get you excited. Nothing else I do today is. Sorry. We did that with relative ease, didn't we? I mean, that took us less than 5 minutes to do with polar coordinates. If you did that in Cartesian, it would involve, trig substitution, and it's doable. It probably takes about 10, 15 minutes to do the other way. All right. Now, this is a picture of a surface, some function of x and y, which we're converting to r cosine theta, r sine theta, which creates like an upper surface, another surface g that creates a lower surface. We're trying to find the volume between these over some polar rectangle. And so this, again, to just remind you what happens here, if you're trying to find the volume between two surfaces, you subtract the two surfaces, which really just breaks down to subtracting the integrals, double integrals. And we can convert to polar and do exactly the same thing. So here's a good example. Find the volume of the solid below x squared plus y squared plus z squared equals 1, and above the cone z equals root x squared plus y squared. So hopefully you recognize the first equation as the equation of a sphere radius 1. So you have this sphere radius 1, there it is. You've got this cone, z equals root x squared plus y squared, which starts at the origin in three-dimensional space, creates this cone shape. We're trying to find the volume of the solid below the sphere, above the cone. So that thing right there looks like a snow cone, right? Does that look like a little snow cone? What's its volume? So how to do this? Any ideas? Any ideas? Sure? You seem kind of... All right.
Get the whole and then subtract the one above the cone.
Do the what?
Find the volume of the sphere and then subtract the volume of the cone.
That's a good idea. Let's think about what's being proposed. If we take the volume of the entire sphere and subtract the volume of the cone, that's not quite a cone though, but you would want to subtract this together. I think that's what you're getting. I don't. Take a look back at this picture that I just had up here. If I'm trying to find the volume of this chunk of stuff right here, does it have a top cap? Yes, it's the F function. Does it have a bottom cap? Yes? And what about the walls of this thing? That's dictated by the region on the ground, right? So as long as you can come up with some top cap and some bottom cap to the solid, and then you can define very clearly what the region is that you're integrating over, then you should be able to get the volume. So let me take you back to this picture. Do you have a top cap? It's just slow, that's it. The top cap is created from the sphere, right? The bottom of that solid is created from the cone. So you have a top and a bottom, don't you? The question is, what's the region of integration? So you have to look at almost like the shadow of that object straight down. So if I take this object and I rotate it and I look at it straight from the top, right? Then I imagine taking this edge straight down to the XY plane. That's my region of integration. Do you all see that?
Is that a circle?
And that's a circle, yes. So again, I'm going to try and draw it on here. If you translate this thing, this red curve straight down, you get some circle down here on the ground. Okay? Do you all see that circle? What we're doing is we're saying, take a point here, plug it in, right? And if I go straight up and I go in between the sphere and the cone, I will be in the snow cone, won't I? Yes? And I have to pick points all from in here and take all those up to draw the whole picture. Yes? Okay, so how are you? I think we've talked about what the region is. How are you going to find it though? Is it the radius? Is it the radius of the sphere? No, it's not, right? It's where the two hit each other. It's where the cone and the sphere hit each other. If you imagine taking that and just going straight down to the ground with it. So to start off, to get my region, I first need to find where these two intersect. How could you do that? How could you find where those two intersect? Do it what? Huh? Set them equal to each other would work, but we would have to solve them both for z and then set them equal, right? Or you can just say, hey, look, to live on the cone, z must be this, right? So just go rewrite that sphere equation and square z, right? This right here is z squared, isn't it? And then equals 1. So you get 2x squared plus 2y squared equals 1. And that means x squared plus y squared equals 1/2. And that's a circle of radius. It's the radius of this circle. Root 2 over 2 or 1 over root 2, right? Those are the same things. That's your radius. Questions? Regular?
That was a neat trick.
What'd I do?
Oh, I mean with the plugging Z.
Oh, okay.
Z squared.
Yeah, and you know, you could even go a little bit trickier than this if you wanted to. If I know I'm going to polar, which I do, I know I'm going to go to polar on this, right? Then I could just replace x squared plus y squared with what here? R squared. And square root of r squared would be r. And so I could replace this. That first equation becomes what? R squared plus r equals 1. That's a quadratic equation. R squared plus r minus 1 equals 0. And then you could do, how would you figure out what r is there? How about a quadratic formula? And you would get a quadratic formula, and one of your solutions would be this. But we didn't do that. So, all right, we good? Can we draw the region on the ground? Okay, so we could do, we know it's a circle on the ground. It has a radius of, do y'all like 1 over root 2 or root 2 over 2? Does it matter to you? Doesn't matter. Okay, I'm going to use 1 over root 2. I'm still boycotting rationalizing fractions. I've been boycotting them for a long time. All right, polar region. As a polar region, theta is going between and r is going between. Theta? 0, 2 pi. R, 0, 1 over root 2. So I'm going to set up my double integral. I want you to pay close attention here. This is the double integral I'm trying to set up. I'm trying to set up the double integral over some region R of f of xy minus g of xy dA. That's what I'm trying to do, right? It's between two surfaces, so I'm trying to find the volume between two surfaces. My upper function, f, is the sphere. And that means I need to solve that for z. So go ahead and do that now. Solve this for z. You get z equals square root 1 minus x squared minus y squared. Now, it should be plus or minus, right? But I'm only doing the plus because I'm looking at the top cap, the top half of the sphere. And then this one's already solved for z, isn't it? So this is my f function. And this right here is my g. So this becomes double integral over r of square root 1 minus x squared minus y squared minus square root of x squared plus y squared dA. That's what it would be in Cartesian. Not only would this suck in Cartesian to integrate, our limits of integration would suck too because they would involve a circular region, so that we would have to break it up into multiple pieces, and we'd have like a top half and a bottom half, and it would just be a mess, like a disaster. That's the value of going to polar. So if I go to polar, which I'm about to do, I'm always just going to remember RD theta. Okay. My function of x and y is now going to get converted to a function of r and theta. Y'all know what we're going to replace the thing in here? Right, we're going to factor a negative out of those. And it'll be just 1 minus r squared underneath the root. Minus, and this is just going to be r. Limits of integration, theta on the outside, 0 to 1 over root 2 here. I would probably distribute the r through now. Anybody have any questions on where I got that from? I'm going to dot this one. So when I distribute this r through, I get r root 1 minus r squared dr d theta. And we should be able to integrate this pretty easily. This one right here, basic u sub. Let 1 minus r squared be u. The derivative of it's out there, kind of. This one, 1/3 r cubed. You're in business. So if you forget this, right, if you forget that r, not only would you be wrong, but the integration would change quite a bit, wouldn't it? 1 minus r squared, root 1 minus r squared, you would do that with a trig sub instead of a basic u sub. And so you'd be doing a lot of work for nothing. So dot, dot, dot. All right, we have one last type of thing we're going to look at in this section, and we're not going to get too heavy into it. I just want you to know it's there. The idea of a type 1 region in Cartesian said that we're going to stick our x's between two constants, and our y values will be stuck between two functions. So as your x changes, your y values may vary between two functions, right? That's type 1 Cartesian. If we do something similar in polar, what we're going to do is we're going to let our theta still be stuck between two constants, so between alpha and beta. So that doesn't change. But instead of saying that the radius has to be stuck between some small radius and big radius, I'm going to say that that radius is a function of theta. The inner radius is a function of theta, and the outer radius is a function of theta. And when you do that, you get a type 1. And what happened with the type 1 over here? What was the major thing that we had to be careful with? What was it? F1 of x and, no. Was it F1, G1? G1, G2, right? What was the major difference between this and like just a rectangle? That we're going to have, or limits of integration were going to be functions, which also forced our hand when it came to the order of integration. We had no choice. We could not switch the order of integration. Same thing's going to happen here. If you have something like this, your outer limit of integration is going to have to be your d theta, because that's going to be stuck between alpha and beta. Then you're going to have dr. Your radius is stuck between two functions of theta, h1 theta, h2 theta. And then this in here, it doesn't change. F of r cosine theta, r sine theta. So you see now, oh, what am I forgetting? R. R. So see, I can't switch these because these are no longer constants. I'm going to give you one example of this. And it's basically the problem that was going to be your problem 3 for your take-home, which I've changed, by the way, if you came in late. There should be a new copy of the exam on the desk. Problem 3 is changed. I like this problem. This is a really, really good problem. A sphere of radius 3, it's actually a solid. Imagine you have a solid ball, all right? And we're going to drill through the ball. And when we drill through the ball, it's going to take some of the material out, and this ball is going to have a new volume to it, right? So here it is. You can look through there, we see, right? So the idea here is that the radius of the sphere is 3. And I come in here with a drill bit that has a radius of 1. But this drill bit, I'm not going right through the center of the ball. That would be too easy to find the volume. Instead, what I'm doing is I'm drilling so that this is the x-axis, by the way, this is the y-axis. My drill bit's coming in here. In the center of the drill bit is here, and the drill bit always runs tangent to the z-axis. So here's my z-axis. My drill bit must always be touching that and going, basically it's going straight into the sphere, right? But it's offset. Do you see how it's offset? What is the volume of the remaining object? That's the question. It's a very difficult question to answer by hand, which is why I changed it. But we can set the integral up pretty easily. Any ideas on how you'd want to do this? Find the equations. You want to find the equations of the sphere and the cylinder? Or, okay, so what's the equation of the sphere? What was our radius? I think on this problem it's 3, right? On this one, I thought take home it was 4, right? Sphere radius 3. So 9, that's your sphere. All right. Cylinder, you want the equation of the cylinder? What is the equation of this cylinder? X squared plus y squared equals 1 would be a cylinder, but that would go through the origin, wouldn't it? Wouldn't that be right up through the center? I don't want it there. Where do I want the center of that thing to be? The center of it should be at 1, 0, shouldn't it? So look, if I'm looking straight down on this, let's say this is my x-axis, this is my y-axis. Here's the sphere, right? Radius 3. My drill bit comes in here like this. Right? Comes in like that, drills out. So the center of my cylinder should go through this point 1, 0. Very good. All you do, remember how we shift things around, right? X minus h squared plus y minus k squared. The h and the k move your center. So this is going to move it to 1, center to 1. Okay? Well, I've done what was requested. It was requested that we find the equations of each one. Now, find the what? The range. How do you mean range? You mean like the polar stuff, like r and theta and all that? I'm okay with that. But I would still like to hear, like, what's the method, like what are we going to do? Like what are we finding the volume of? What do you want to find the volume of here? So you're trying to go about this problem by actually finding the volume of what we took out? Yes? Do you know the volume of the sphere if we never took anything out? Yes, right? Yep, go ahead.
It's something where she said you can just find the volume of the cylinder and subtract it from the sphere.
I agree, kind of. Okay, yes, we all can find the volume of a sphere, right? There's no calculus involved in that. We just look up a formula for it and we're done, right? If we know the radius, we know the volume. So we take that answer and we subtract from it the volume of the cylinder, kind of. Because the problem is that, what's the problem?
The cylinder goes on.
Yeah, see, the cylinder keeps going up. So where do you cut it off? At the top, right? What's the top look like, though? Let me see. I thought I had done this where you could see it. Doesn't look like I did. Oh, here we go. That's what I wanted to do. If I take this all out, Yeah, it's hard to see that. I'm going to try and zoom in on this. I hope this works. If I rotate this, yeah, that's going to work. You see, that top edge of the cylinder is part of the sphere, isn't it? You have to account for that. So let me go back and ask you a question. Do you have a top cap and a bottom cap? Yes? Right? The top cap of this part that we drill out is the sphere. What's the bottom cap? The sphere on the other side, right? Now I could make my problem a little easier by, instead of going on the sphere to the other side, I could just use the XY plane as the bottom and then find that volume and double it. You don't want to do that? I like that idea. Okay, so the top part's going to be the sphere. The bottom part's going to be the XY plane, which is z equals 0. And the only thing left is what's the region of integration. So let me kind of write what I've said down here. I'm going to go with the approach. My approach is going to be that we have a top function, f of xy, which is the sphere, but I have to solve it for z, don't I? Oh, we love seeing x squared minus y squared, don't we? And then the bottom function, which is going to close off the bottom of the solid, we all agreed would be 0, right? And now the region of integration. Isn't the region of integration that circle? The trouble we have right now is putting that into polar coordinates, because I'd love for this problem to be in polar coordinates. Is that a rectangular polar, is that a polar rectangle? Is your angle between two constants and your radius between two constants? So if I look at this angle, if I rotate, let's say to here, is my radius between two constants? Imagine a dotted line right there. So I'm allowed to walk from here to here, right? If I rotate a little bit more to here, is that radius still the same? It's not, right? If I rotate this much, I'm allowed to walk out that far, but if I rotate further, I can't go as far, can I? And if I rotate even more, it's even shorter. Agreed? Somehow, how far I walk out is a function of how far I rotate. And this is what I was just getting at a second ago with that picture that we had, where I said we had h1 of theta, h2 of theta, right? Your angle's allowed to change, but how far you walk out changes when your angle changes. That tells me it is not a polar rectangle. So how in the hell do we get the restrictions that we need? We still need some restrictions on theta, and we need some restrictions on r in order for us to convert to polar, right? So we sit here and we look at it and we think about it, and then we realize, wait a minute, hold on. What do we know about that circle? What I know about that circle is that it follows this equation, right? That's the equation of that circle. In two-dimensional space, that's a circle. In three-dimensional, it's the cylinder. But do you agree? Now I'm just going to mess with this for a second. I'm going to expand this out, right? Anybody see anything in there? Think polar, think polar. X squared plus y squared is r squared minus 2, what's x in polar? R cosine theta, got that? And then 1 and 1 on both sides, subtract 1, and you get equals 0. Now remember what we're trying to do. We're trying to find restrictions on r and theta. theta should be stuck between two constants, but my radius should be stuck between two functions of theta. Can you solve this equation for r? It's a quadratic in r, isn't it? What can you factor out of each of these? R. So if I have to factor out an r, I get r, and then r minus 2 cosine theta equals 0. Set each one of these equal to 0. What do you get? R is 0, and r minus 2 cosine theta is 0, which means that r is equal to 2 cosine theta. So in order to draw this circle in polar coordinates, you need r to be 0 or r to be 2 cosine theta. Now think about r being 0. If r is 0, does that draw this circle? No, if the radius is 0, where are you? Right there, this point right here. Okay? That point is taken care of by that equation right there. Then this should draw the rest of the circle. Let's see if it does. Are y'all with me? Let's see. Let's let theta, just for example, let's let theta, I'm going to do a good old-fashioned t-table. Theta r. If theta is 0, what's cosine of 0? 1. 2 times 1? 2. So if my angle is 0, then I should walk out 2. So if my angle is 0, I should walk out 2 and draw a dot. If my angle is pi over 4, how far do I walk out? Well, cosine of pi over 4 is root 2 over 2 times 2. It's just root 2. Root 2 is about 1.414, something like that. So 1.414 is about this far, right? But I'm supposed to walk out that far when I'm aimed at pi over 4. Pi over 4 is 45 degrees. Wow, that's right there. Do y'all see that? What would happen, and this is kind of an absurd case, but what happens if my angle is pi over 2? So I'm aiming straight up and I'm saying, okay, how far do I walk out? Cosine of pi over 2 is 0, so it says don't go anywhere. So guess where you are? Right here. Got it? So far, I can draw the top half of this circle by letting my theta go between 0 and pi over 2. Understand? How do you think we're going to get the bottom half?
Negative.
Go negative. So if you go down and you start letting theta go negative values all the way to negative pi over 2, you'll draw the bottom half. So do y'all kind of get this? My restriction on theta is going to be between where and where? Negative pi over 2 and pi over 2. And then my restriction on r, how far I walk out, always has to be between 0 and 2 cosine theta. This is h1 of theta. This is h2 of theta. Now this is a true function of theta, isn't it? Theta actually makes a difference here. This one doesn't make a difference. 0. Questions? This is what we were looking for, right? This is what we were hoping for, is something that would draw this region. And I believe we've got it. All right, now double integral time. What we were going to do is we were going to find the volume of the part that was drilled out. And so we decided to take a look at the top cap being the sphere and the bottom being the xy plane and then doubling the answer, right? So the part that we're drilling out, and I'm going to make sure I'm clear on this, the volume of drilled out part of the solid is 2, I'm going to erase this, is 2 times the double integral I'm going to polar. R d theta. That has to be this order because theta is between two constants. They were negative pi over 2 and pi over 2. My radius was stuck between 0 and 2 cosine theta. And then it was just the f function minus the g function. Here's the f function. But to polar, what is that in polar? Root 9 minus r squared, right? Minus 0, so it doesn't matter. And that's it right there. And then you would go and integrate that. But I'm not going to say dot, dot, dot here. This we could not do by hand. The first integration is easy. The first integration is a basic u sub. But the second integration, I believe you would wind up getting something like you're trying to integrate, forget about constants, but I believe it's something like square root of like 9 minus 4 cosine squared, if I remember correctly, something like that, d theta. Something like that. You're trying to integrate that. And that ain't happening. So that's why I changed the problem on the take-home. Questions? Your problem that is on your take-home exam is very similar to this problem. In fact, I probably gave you way too much here. But your surface on top and bottom is a little different, and it makes the integration possible. It's going to be a little messy with the integration, but all within, fair game stuff. All right, so what would we do now to find the final answer? If we were able to find this volume, right? We got it. We double it here already, right? Find that answer. We take that answer and subtract it from the volume of a sphere, which you have to go figure out. The difference on your take-home problem is since it's not a sphere, right? You don't have a formula for it. And therefore, you have two problems that you have to do here. You have to find the volume of the paraboloid first, which is a double integral. Then you come and take this away. Do you understand how that's two different problems? Okay. Enjoy. All right, that's it for that section. We are going to very briefly talk about 12.4. And when I say brief, I mean we're going to be done here in 20 minutes, I think. So some of the applications. We can get really, really heavy into applications in this class, or we can actually finish the book. And I choose to finish the book as opposed to do heavy applications, only because everything we've done so far is enough for you to do this. It's just a matter of making the connections between, a physics class and a double integral in there, and then doing the double integral, which is what we're trying to show you here. But here are some of the things you can do with double integrals. Suppose you have a lamina. A lamina is like a two-dimensional sheet, a piece of paper. That's a lamina. All right? And it has some weird shape to it. Here it is. And then the density at every point, right? Remember, density is mass divided by area in this case, because it's two-dimensional. So you're looking at, what you're trying to do is you're trying to figure out what the density is at each point, and then you can ask questions like, well, what's the mass of this thing? Okay, what is its mass? So what we deal with in terms of laminas are what are called homogeneous laminas, which are laminas like a sheet of paper, where we assume basically the density is always the same. If you cut out a 1 inch by 1 inch square from anywhere here, take two of them, two 1 inch by 1 inch squares, and weigh them, they should weigh about the same, right? Because we're assuming the density of the paper is the same throughout, uniform, homogeneous. And then you have laminas that are non-homogeneous, which would be something where the density varies throughout the lamina. And that's what we're interested in. What if you have a more complicated lamina where as you look through it, its density changes? So suppose the density is variable, all right? Then the total mass of the lamina is the sum of the mass at infinitely many infinitesimal rectangles. So you're basically cutting up this lamina into a bunch of little tiny rectangles, and you're finding the mass at each one. And if density, if you know the density at every point, so that has to be given to you, the density at every point, density being mass over area means that you can solve this for mass, and mass would be equal to density times area. Density you're given is a function. Here's your density function. So density you're given, area we know, because that's what we've been doing. So you're adding up all these little masses, which means you add up the density times the area. And replace that with F, and that's what we've been doing, right? So all that's changing here is that we have the function actually means something now. F of xy, if it represents a density function of a lamina, then doing that double integral over that region gives you the mass of the object, mass of the lamina. If instead we like to do something that involves electromagnetism, something like that, we could look at a lamina again, a flat sheet of paper, and we could say, hey, look, check out this sheet, whatever it is. It has a charge at each point. Some charge density is what they call it. Then if you look at and you're trying to find the total charge on this lamina, then what you do is you multiply the charge density times the area, and you get the charge at each little infinitesimal. And you add those up, you get the total charge. So again, it's the same concept. What is the meaning of this function? In the previous example, rho of xy was a density function. In the second example, it was the charge density. So if you do this double integral, it gives you the total charge. Again, all I'm trying to do is trying to get you to see that in a physics class, if we give that function f, which is what we do in this class, f, if we give that some meaning, then we can correspond it to either like total charge or total mass. And there's no restriction. It doesn't have to be just those two functions, but those are common ones. So a lamina is formed by the region bounded by these curves. The density is given by this density function. Find the total mass. So this one's going to go fast. I have a lamina 1 minus x is that. Y equals 1, x equals 1. So y equals 1 looks like this. X equals 1 looks like this. Everybody see the region bounded by those three? Okay. The density at a point in that lamina is x times y. So if I come out here and I say, I don't know, I pick the point 3/4, 3/4. That point lives in there, doesn't it? What's the density at that point? What's the density of the lamina at that point? It's the x times the y, right? X times y. So it's 9/16, whatever they're measuring it in, right? But if I change and I move this to 1/2 and go up 3/4, then now it's changed, right? Now it's 3/8, different density. So this lamina, its density changes throughout the shape, throughout the figure, and we're trying to find its total mass. So all it would be is what? Let's see how many of you got this down. See a lot of glazed staring into nowhere. So How do you want to do this? Do you want to go polar? Every time I say, do you want to go polar, I always think of, do you want to go postal? You've heard that before? Postal, like go crazy? Isn't that a term that they use for that? Go nuts. How do you want to do this? Type 1? Type 1 region? Okay, I agree. We're integrating. What are we integrating? What's our function? XY. Since it's type 1, my x's are bounded between two constants. What are they? 0, 1, right? 0 to 1. My y's are bounded between two functions of x. This one's the bottom one. This one's the top one. So the bottom one is 1 minus x. The top one is 1. D y dx. If you can compute that, you've got the mass of the lamina. All right? I'm not going to. Questions? This is the same exact problem. Everything's the same, except instead of using a density function, using a charge density. So the only difference is the answer means something different, right? If you find this integral, that answer would represent the total charge on that lamina. Now, along with being able to find the mass of a lamina, you can find what's called its moment. Now, this is a physics concept. And we use the moment to compute something else. So first, let's talk about what the moment is. Same lamina, right? There it is. Blah, blah, blah. It's got a variable density. So we still have the charge density, or sorry, the density function right here. You see it? But we've added one thing to it. You see the y right there? Y times the density function. If we compute this, it's called the moment of the lamina about the x-axis. And we use capital M subscript x to represent the moment of that lamina around the x-axis, or about the x-axis. If we switch it, and instead of multiplying by y, we multiply by x, we call that the moment of the lamina about the y-axis. So physics again, moments are basically the mass of the particle times the distance to an axis. Now, why is that useful, computing the moment of a lamina? Well, the next formula. If you have a lamina, same thing, has a variable density. These are all in your book, by the way, and they're all in your notes too. Then one of the most interesting things to find, in terms of a lamina, is its center of mass. Especially if the lamina does not have the same density throughout. Like if you have a flat sheet of paper like this, a rectangle, and it's homogeneous, which means the density is always the same, the center of mass is pretty obvious, right? It's just the center of this. But if this is no longer homogeneous, then the center of mass could be just about anywhere, right? And there are even some objects where the center of mass isn't even on the object. A boomerang is an example of an object that has a center of mass outside of its space. And another one you could take is like just a disk like this. Its center of mass is there, right? Even if it's homogeneous. So finding the center of mass is computed. The center of mass is a point. It has an x and a y coordinate. We call it x bar, y bar. And look at what you do to compute the x and y coordinates. To compute the x coordinate, you have to take the moment and divide it by its mass. To find the x coordinate of the center of mass, you take the moment about the y-axis and you divide it by the mass. Remember, this was the moment, right? I know everyone's tired, but don't help them out. All right, thank you. Right, that was the moment formula, and then we just 1 over mass means divide by mass. But what was mass? Yeah, but wasn't the mass a different double integral? So in order to find the x-coordinate of a lamina, center of mass, you have to do 2 double integrals. One double integral gives you the moment, and you divide it by another double integral, which gives you its mass. And then to find the y-coordinate, it's the other moment divided by the mass. So if you're given a problem where you're asked to find the center of mass of a non-homogeneous lamina, you have to compute 3 double integrals. You have to find the mass, because you need it for both of these, and you need to find both the moments. Here's an example where you're asked to find the center of mass of a region bounded by some things, and then I give you the density function here. What I wanted to do with this was to just show you, like, this is the lamina. It has a variable density. So can you see that the darker shades represent where it's more dense, and the lighter shades where it's less dense? How dense it is depends on the x value. For this particular density function, the x value dictates how dense you are. So the bigger x is, right, the bigger your density is. And I actually did this 3-dimensionally, so you could actually pop it out of here. And whoa. You could kind of get an idea of how much more dense that object is out here towards this edge with the height. Now, it's not 3-dimensional, but it just gives you some idea of how much of this object's density is over here. So its center of mass should be way over here somewhere, shouldn't it? It's not going to be right in the middle. It should definitely not be, right? Center of mass should not be like right there. It should be this way. So to do it, I only have 2 minutes, 3 minutes, 4 minutes. This was y equals negative 2x plus 6, and this is y equals x. So that's, if you were to draw this region out, that's what you would get. And so you would need your limits of integration. This would be a good type 1 region. So you should go double integral. Let's do the mass first. Mass would be double integral where to where? Well, you have to figure out what's your bound on x. 0 to wherever they hit each other. So you set those two equal to each other, okay? It's 2, all right? I think it's 2. 2 in here, 2. Yeah, so if you plug in 2, you should get. And then what's the lower and upper bounds here? Y equals x on the bottom and negative 2x plus 6. Now for mass, what am I integrating? Just the density function, x squared. dy dx. You figure out what this is, and you get a number, right? That's your mass. Put it to the side. You'll need it later. Then you come in here, and you do the moment, right? So if I want x bar, it's the moment about y over mass, which is 1 over mass times the double integral of what? What changes? These are opposite. I'll go back to the moments. So look, moment, a moment about the y-axis, you use x in here. A moment about the x-axis, you use y. That was it. So it would be x times that, so x cubed. dy dx. What about the limits? Exactly the same. So you're doing almost the same integration, right? Except you're doing x cubed instead of x squared. And then when you do y bar, it's moment about the x-axis over mass, which is 1 over mass double integral. Those limits still stay the same. And now this time, instead of x cubed, it's yx squared, or x squared y, dy dx. Now that integration is going to be a little different, right? Because now you have a y in there.
Does the dy dx always stay the same?
Yes, because it was a type 1. Because we chose to do it as a type 1 region, right? We decided to go this way with it. You could do type 2, but it would suck because you'd have to break it into two pieces. Yes?
What section did you use polar coordinates?
You could use, if this region was, if that region looked like you should do it polar, then yeah. What about on the take-home? Aren't you asked for a mass? Yeah, but it's not, yeah, I don't think that's, whoa, do I not give you, whoa, there's no, I don't give you any restrictions. What the hell? We need to fix that. I didn't give you any restrictions on that, did I? Okay, hang tight, or else you won't be able to do number 4.
On the X bar and the Y bar,
Yes?
maybe on the notes it's multiplied by Y for X bar.
Mm-hmm.
Inside the integer, when you did X.
What did I do? Hold on a second. 0, 0, 1. Okay. For X bar, where did I reverse it? You sure?
On my notes, no, my notes like a different than yours.
What does yours say?
On the X bar, it's multiplied by Y.
Well, it was like an actual shape, like a recognized shape.
Who has the book? I do. Okay, so look, on number 4, let's fix that first. On number 4, the region is the region, this is y equals e to the x. This is 1, this is 0. So it's the x-axis. Okay. I don't know where I want to do this. The moment equations are correct. Does that match what you have on your notes? The moment equations, there they are. Yes? So the moment of the lamina about the x-axis, it's y times the density function. Moment about the y-axis, x times the density function. And then x bar is the moment about y divided by m, which is 1 over m, and then this right here is the moment about y. So x times the density. Is that not what I have there?
Yeah, you're right.
So it's okay there? I'm just making sure it's not a typo.
No, yeah, it's
Okay. And then the y bar is the moment about x over mass, which makes that a y. Okay, did I resolve number 4? As far as what the region is. Now on number 4, doesn't it ask you to compute the moments of inertia also? So you should be able to do part A. You should be able to do part B. Part C is moments of inertia. And just look in the notes, okay? There's two more formulas. Moments of inertia. There's these 3 formulas. Moment of inertia about the x-axis is almost like the moment about the x-axis. Instead of multiplying by y, you do y squared. The moment about the y-axis, instead of multiplying by x, you do x squared. So again, it's very similar. Now, anyone know what the moment of inertia is? It's if I take, I'm sorry, I'm keeping you late. If I take this lamina, okay, flat sheet, it has a mass to it. And let's imagine that I want to take it and rotate it around the x-axis, three-dimensionally, right? It has mass, so I have to push it, right? And anything that has mass resists motion, doesn't it? So if I go to push this, it's going to have a resistance. That's your moment of inertia. If I move this further away from the axis, it changes its moment of inertia. Its resistance to motion. So the last question there is to determine with calculus if it is easier to rotate the lamina about the x-axis or y-axis. So that means you need to calculate these two moments of inertia and compare your two answers to answer that question. I'm going to leave that to you to figure out. I want you to think about it, and if you can't figure it out, I want you to look it up. Think about a door. Think about a door. If you go to open that door, if you pull it by the handle, it's going to be easier than pulling it by a handle in the middle of the door, right? So maybe that helps. I don't know. Okay? I guess have a good day.